All right, let's get into a physics problem that seems so simple, you'd think the answer is obvious. But as we're about to find out, what your gut tells you should happen and what the laws of motion say actually happens, well, they're two completely different things. So picture this. You've got a simple rod standing straight up on a perfectly frictionless floor. We just let it go, and it starts to fall. Now, what does that fall look like? I mean, does the bottom end just kind of scrape along the floor as it goes down? Your intuition, your gut feeling, is probably screaming that it just pivots, right? The bottom stays on the floor, sliding along until the whole thing is flat. That makes perfect sense. But the physics tells us something so much weirder is going on. It says the rod actually hops. It lifts completely off the floor before it ever lands.
Okay, let's really dive into this setup. Let's try to figure out why our first guess, our totally reasonable intuition, is actually leading us astray.
Now, the conditions here are super important. We're talking about a uniform rod, meaning its mass is spread out perfectly evenly. The floor is totally slippery, absolutely no friction, and we're releasing it from a complete standstill. And yeah, this is what almost everyone assumes. It feels right, doesn't it? I mean, gravity is pulling the whole thing down, so shouldn't that force keep the bottom of the rod pinned to the floor the entire time? To really see what's happening, we've got to look past our gut feeling and look at the actual forces and energy involved. And it turns out, we only need a couple of fundamental physics principles to crack this whole thing wide open. And don't worry, we don't need any super complicated high-level stuff here. In fact, there are really only two key ideas we need to understand to solve this puzzle: the center of mass and the conservation of energy. Just think of the center of mass as the object's true balance point. And here's the golden rule for our problem. If you don't have any outside forces pushing or pulling on an object in some direction, its center of mass cannot accelerate in that direction, period. And that right there is our first massive clue. Since the floor is frictionless, there's nothing to push the rod sideways, and that means its center of mass can only move one way, straight down. No left or right motion at all. Okay, next up is a principle that's just fundamental to all of physics. The rod starts out with a bunch of stored up potential energy, just from being upright. As it falls, that energy has to go somewhere, right? It gets turned into the energy of motion. But here's the cool part. That energy gets split two ways. Some of it goes into the rod just falling downwards. That's what we call translational energy. And the rest of it goes into the rod spinning as it falls. That's its rotational energy. So we're starting to get a handle on the motion, but we've been ignoring a really important piece of the puzzle. There's one force we haven't talked about at all, and it's the one thing keeping this from being just a simple freefall problem. Think about it. It's a force you and I are experiencing right now. The reason you're not falling through your chair and through the floor is because the floor is actively pushing back up on you, and that push has a name: the normal force. Physicists call this a constraint force. Its whole job is to maintain a boundary, to constrain the rod so it can't just sink into the floor. But here's the catch with constraint forces. They're not constant. They only push as hard as they have to. This is just good old F equals ma. The total force on the rod is gravity pulling down, that's mg, minus the normal force pushing up from the floor, that's n. And whatever's left over from that tug-of-war is what actually makes the rod accelerate downwards. And this, right here, is the key question. A contact force can only exist if there's, contact. So what happens to that force at the exact instant the contact is broken? And there it is. That's the aha moment. If the rod lifts off, it means the floor isn't pushing on it anymore, not even a little bit. That upward normal force, N, has to drop to exactly 0, and that is the precise condition we've been searching for. Okay, now we've got all the pieces. We can finally combine what we know about energy, forces, and that center of mass motion to find the exact angle where this mysterious liftoff happens. So, the liftoff happens at the precise moment the rod's center of mass starts accelerating downwards at g, the full, unhindered acceleration of gravity. It's no longer being held back by the floor. It is effectively in free fall, even as it continues to rotate. And now we can put these ideas into math. It's really just a four-step process. We take our energy equation, we use a little calculus to figure out the acceleration, we set that acceleration equal to g, and then we solve for the one thing we don't know, the angle. And after all of that, the answer is just beautiful. And so simple. Liftoff happens when the cosine of the angle is exactly 2/3. This means the rod hops off the floor when it's only tilted at about 48 degrees. It's not even halfway to being horizontal yet. So, okay, we've solved the puzzle, The rod hops. It's a cool result. But what's the big takeaway here? What does a problem like this really teach us about the world?
Well, for one, it's a perfect example of how our intuition can sometimes fool us, and why we have to trust the fundamental principles of physics. We've learned that forces we usually take for granted, like the normal force, are actually changing all the time. And we've seen how a simple idea like the center of mass can cut through a complex motion and make it simple.
And that's really what's so cool about physics, right? It gives us this completely new way of looking at the world. So the next time you see a ladder slip down a wall, or even just a book sliding off a table, you might just stop for a second and wonder, what's really going on there? What's hiding just beneath the surface?